So a really common workout in the gym is obviously the pull-up. Now, before we demonstrated two diagrams to you, there are two ways you can do a pull-up. Either you can do a pull-up while stationary, the appropriate way, or you could use your legs to swing up and down before doing the pull-up. We noticed that it is much easier to do a pull-up while swinging. This has to do with energy conservation. So let's assume we have a force diagram like this, where we have tension with your arms keeping you up and gravity pulling you down. It's logical that to get to the top of the bar, the force that you pull up with must exceed the gravitational force. Now, let's assume that you're going up at a constant velocity, which would mean acceleration is zero. If we were to analyze this using work, we would simply say that the work required to get to the top of the bar would be the change in potential energy. Assuming when your arms are fully stretched, that's the base, that's the bottom of the bar, the amount of work you have to put would be mg times the difference in height. When you're swinging, however, you have a base kinetic energy. So it'd be less work because it would simply be the potential energy required to get to the top subtracted by the initial kinetic energy. That is why when you're doing a pull-up and swinging, it is easier to do because you have to exert less work as you are subtracting the initial kinetic energy from the change in potential energy.
The next workout we will be looking at is the deadlift. The deadlift incorporates the principles of torque. As we learned in class, torque is equal to a perpendicular force times the radius. In this case, the perpendicular force is Ramirez's arms exerting a tension force on the bar, whereas the radius is the distance from the base of the deadlift apparatus to Ramirez's arms. As we know by Newton's second law, the torque must be greater than the cross product of weight times total radius in order for the weight to be accelerated upwards. Given this information and assuming the same acceleration of the weightlift apparatus in both situations where Ramirez's arms are both close to the base and far from the base, we know that the perpendicular force of the first one times the radius of the first one equals the perpendicular force of the second situation times the radius of the second situation. Given that Ramirez's arms are further away in the second situation, but the torque is the same, the perpendicular force of Ramirez's arms is less when he holds the deadlift apparatus towards the weights.
For our last workout, we're going to look at some stair jumps. So the I in the situation jumped twice off the block. In the first jump, I landed and bent my knees. In the second jump, I landed with stiff, straight feet. I received pain from the second jump. Before we look into this problem, we must first analyze and understand the properties of momentum and impulse. Impulse is equal to the change in momentum over the change in time. So the normal force is greater than gravity in both these situations. However, the normal force is greater than gravity because it has to decelerate you, and it has to therefore be greater than gravity. In the case of the first jump, when I bend my knees, the change in time is about more than a second, which is why the force exerted on my knees is not that great. However, in the second jump, the impulse time was less than about 0.4, 0.5 seconds. This had to do with the fact that my legs were not bending, they were straight, which meant my toes hit the ground earlier instead of bending versus bending my knees and having my whole feet touch the ground gradually. This resulted in a higher force exerted on my knees, which caused pain.